All right, we're going to talk about molecular geometry. As with the last time, this will be broken up into several short lectures so that you can take a break. If you need to stop in the middle of it in order to write some things down, please do so by just hitting pause, and we'll just keep going. All right, the first question. A student draws a Lewis structure for carbon tetrachloride and concluded that the bond angles in the CCl4 molecule must be 90 degrees. Do you agree? If not, draw an accurate representation of the molecule and identify what the bond angles should be. Well, actually, the bond angles in carbon tetrachloride are not 90 degrees. The shape of the molecule is tetrahedral, and the bond angles are 109.5 degrees. And this comes as a consequence of the VS-EPR theory. We can take a little look at this picture, and we can see that, in fact, the angles are not 90. And the reason that they are 109.5 I'll get to in just a few minutes. The next question says, well, do you predict the bond length in carbon tetrafluoride should be shorter than, longer than, or the same as the bond length in carbon tetrachloride, and then justify your prediction? All right, I am saying that it will be shorter than the bond length in carbon tetrachloride, and the reason is the atomic radius of fluorine is smaller than the atomic radius of chlorine. Therefore, the bond length should be shorter. All right, let's take a look at this tetrahedral configuration. We've got one atom in the center, and we've got four other atoms that are identical and that are equidistant from the center molecule. So you can see that in the drawing on the right. You got the carbon in the middle, and then forming a four-sided pyramid, you have hydrogen, hydrogen, hydrogen that forms a pyramid. And it doesn't really matter how you orient this thing, it's still the same on all four sides. And we get 109.5 degrees between hydrogen to carbon to hydrogen, no matter which ones you pick. And the bond length is 108.7 picometers. Now, we really want to know what this bond angle is between any of the four substituents. And it could be hydrogen, chlorine, fluorine, whatever. It doesn't really matter. All right, this part here is not in your notes. You don't really need to write this down, but I think as a student of chemistry and as a teacher of chemistry, it would be the wrong thing to skip this. So you need to know, where does this bond angle come from? All right, we're going to create a tetrahedron by joining the opposite vertices on the face of a cube. And to simplify the arithmetic, we're going to assume the cube has sides of length 2. All right, so I create the tetrahedron by connecting the opposite vertices, and you can see the shape of the tetrahedron inside that cube. And we want to let O be the point at the center of the cube, and it's equidistant from all 8 vertices. So we're going to construct this triangle OPQ. Okay, and so it's going to look like this. O is in the center, and I can construct this triangle OPQ. And I'm trying to find out the nature of these angles. All right, so let's consider this triangle OPQ. And I want to let R be the midpoint of the side PQ. All right, now since the sides of the cube are length 2, we can use the Pythagoras' theorem to get the absolute value of the length of PQ, and that becomes 2 times the square root of 2. And we can see why that is by knowing this is a 45, 45, 90 triangle. Now, since O is at the center of the cube, that makes the length of side, or the length of the leg OR, equal to 1. And from this diagram, we can look at the tangent of the angle ROP. And that would be, of course, the tangent is the opposite over the adjacent. So I get 2 times the square root of 2 divided by 2, because I'm cutting it in half, divided by 1, the opposite over the adjacent. And that's just equal to the square root of 2. So the angle ROP now becomes 54.73 degrees. And that makes angle POQ, which is our desired angle, twice as big, or 109.47 degrees, and we round that to 109.5. And that's where this comes from. And again, we can look and see this angle, POQ, is the angle that we are trying to find. All right, that information will not be testable in terms of the deriving this bond angle. Knowing what the bond angle is will be testable. All right, now let's take a look at the carbon dioxide molecule. That shape is going to be linear. And of course, if it's linear, the bond angle is 180 degrees. All right, now we want to identify the shape of the sulfur dioxide molecule, which is not the same as the carbon dioxide molecule. On first glance, you might think that it would be, but we can justify our answer based on the Lewis structure for sulfur dioxide. And it's bent, and the reason that it's bent is because the central atom, which is sulfur in our case, has a lone pair of non-bonding electrons. And these non-bonding electrons, they push away the bonding pairs because they're all the same negative charge, and that pushes them away and down, and that results in a bent shape, which looks like this. All right, now we have a few other shapes we want to take a look at. The shape of the sulfur trioxide molecule is trigonal planar, and it has bond angles of 120 degrees, and we can see what that looks like right here. The sulfur's in the middle. The 3 oxygens are arranged equidistant around the sulfur, and so this becomes trigonal, or a triangle, where all the atoms lie in the same plane. That's 120 degrees. All right, the shape of the the methane molecule is tetrahedral, which we talked about. The bond angles are 109.5 degrees. And this is just sort of a different view of the same thing we were looking at a few minutes ago. When we look at phosphorus pentafluoride, the shape of this is trigonal bipyramidal. And this has bond angles of 90 and 120, and we can see that when we look at the picture. All right, the phosphorus is in the middle, the 5 fluorines are in blue, 3 of them are arrayed in a planar fashion, in a triangle fashion around the center. And then we have 1 at the top and 1 at the bottom. So the angle that the fluorines make, the top down to the middle phosphorus out to the side, that's a 90-degree angle. But the 3 that are on an equatorial or an equator basis, those are all 120 degrees apart. And we take a look at our last one. The shape of the sulfur hexafluoride molecule, that's going to be octahedral, and it has bond angles of 90 degrees. And when we look at this, we can see that. We can see we have 1 item in the middle, that's our sulfur. We have fluorines all around in a plane, and then 1 up on the top and 1 coming down the bottom. And there are going to be 8 sides, 4 on the top and 4 pointing down towards the bottom fluorine. All right, now we want to draw the Lewis structure for each of the following molecules, and we want to identify the shape and the bond angles. If we take a look at carbon disulfide, this has a symmetrical shape, and the shape is linear, and so of course the bond angle for a linear molecule is going to be 180 degrees. When we look at boron trifluoride, we see we've got a different sort of a shape. this is going to have the familiar trigonal planar shape where the bond angle is 120 degrees. Let me encourage you, at this point, you should be drawing these molecules out. And these have a combination of the lines that indicate the bonds between the different atoms, and then the double dots indicating the non-bonding pairs. When we look at silicon tetrabromide, this is going to be very similar to a methane setup. So I've got the silicon bonded to all 4 bromines. The shape, of course, is tetrahedral, and the bond angle of tetrahedral shape is 109.5. A couple more. When we look at arsenic pentachloride, we see, hey, this is something we've seen before. This looks a lot like the phosphorus. This fact is phosphorus pentachloride in the model, but arsenic pentachloride would be exactly the same shape. The shape would be trigonal bipyramidal. The bond angles are 90 degrees and 120 degrees for the same reasons we talked about a moment ago. And then selenium hexafluoride would look like this. This looks very familiar that we've talked about when we did sulfur hexafluoride. And so the shape will have the same configuration, which is octahedral. The bond angle will be 90 degrees. Now, the last question on this particular slide says, what does VSEPR stand for? That's a real catchy name. Valence shell electron pair repulsion. We say the word Vesper as if it was an Anglican or Episcopalian church service, but it's really VSEPR because the valence shell electron pairs repulse each other, and getting this repulsion to a minimum value is what's going to drive the shape. Okay, now let's talk briefly about this Vesper model. The electron domain can consist either of a bonding pair or a non-bonding pair. And each of the multiple bonds in a molecule constitutes a single electron domain. Doesn't matter whether it's a single bond, a double bond, or a triple bond. These are all considered to be single electron domains. All right, the Vesper model is based on the idea that electron domains, they're all negatively charged and therefore they repel each other. And the best arrangement of a given number of domains is the one that minimizes the mutual repulsion between all of them. Once I can get that mutual repulsion to come into some sort of equilibrium, I have studied up on a shape. And we'll take a look at all of these. There's quite a number of them. The next question says, what's the difference between electron domain geometry and molecular geometry? Use the water molecule as an example to explain. All right, these tables, 8.7 to 8.9 on page 342, 343, that's our book. That's not the other book. This is our book. So I encourage you to go look at these. The domain geometry is the arrangement of the electron domains, both bonding and non-bonding, around the central atom. The molecular geometry, on the other hand, is the arrangement of only the atoms. Never mind the domains. We want to look at just the atoms. What shape do they give? And then part D, for each of the following molecules on the following slide, we're going to count the bonding and non-bonding electron domains around the central atom. We're going to identify the electron domain geometry and the molecular geometry. Okay, so for example, here's our water molecule. You see we've got the oxygen and the 2 hydrogens. That looks like tetrahedral, but I'm only going to consider the actual atoms, and when I do, I see that that configuration is bent. All right, so we're going to stop here. We'll take a look at this on the following video.